Yeah.
Sounds good.
Okay, yeah, now we're live on YouTube.
All right.
Hi, everyone. We'll get started in a minute or so. Okay, I think we can get started if that's okay with you, Tiago.
It is. Yeah,
Great.
let's go.
So welcome, everyone. Very pleased to welcome our seminar speaker today, Dr. Tiago Bilo. Dr. Bilo is a postdoctoral scientist at the Scripps Institution of Oceanography at UC San Diego. He is a seagoing oceanographer interested in large-scale ocean circulation and its connections to our climate system. He received his bachelor's and master's in oceanography from the University of Sao Paulo in Brazil, and his PhD in meteorology and physical oceanography from the University of Miami. His research interests include mesoscale processes such as eddies, boundary currents, deep ocean circulation, and climate dynamics and variability of the meridional overturning circulation. Today, he will speak about pathways of the North Atlantic deep water in the North Atlantic subtropics, structure and recirculation dynamics. So Tiago, the floor is yours.
Okay, thank you, Katie, for this nice presentation. I will share my screen now with you guys. Can you see my slides? Well,
yeah, it looks good.
All right, great. So thank you for inviting me. I'm really happy to talk at NCAR and UCAR. So today, as Katie said, I'm working at Scripps with Yama Stranel, working on the subpolar North Atlantic overturning circulation. But this particular piece of work that I'm going to show you, I developed with my former PhD advisor, Bill Johns, on the North Atlantic deep water interior pathways in the North Atlantic subtropics that we developed at Rosenstiel School of Marine and Atmospheric Science at the University of Miami. So what I wanted to show you guys today is how the lower limb of the AMOC looks like. So this is an schematics of the North Atlantic overturning circulation, where we have the Gulf Stream going northward, bringing warm and salty waters to the subpolar North Atlantic, where the atmosphere can take the heat from the ocean, and this now cold waters can convect in the subpolar North Atlantic and Nordic seas, sink down, and enter in the western boundary current, the boundary current system, and can finally be brought back in the deep ocean by this lower limb, cold lower limb of the AMOC, shown here by the deep western boundary current in blue. Now, what I want to also show here is that this pathway is not exactly this as simple as shown here, but as well as consists of multiple recirculation gyres and interior pathways. So what do you know about it? Just to contextualize my talk here, once these waters that convected in the Nordic seas, so the Nordic seas overflow waters plus the deep waters formed in the Labrador Sea sink down and enter the western boundary current system, it starts flowing with the southward. And once it gets around 50 north near the Flemish Cap, in this area here, two things can happen. One, obviously, it can continue flowing southward with the deep western boundary current, but significant amount of this part of this water can recirculate back into the subpolar gyre or enter the interior of the ocean. And as Susan Lozier described in the late 90s, we're using climatological isopycnal depths. This pathway of waters into that left the western boundary and entered the interior of the ocean. It's within this a anticyclonic circulation that looks more or less like in these schematics done by Gary and colleagues in 2011, where these waters recirculate anticyclonically, flow into the within the so-called Newfoundland Basin to the west of the mid-Atlantic ridge, and connect with a well-known quasi-zonal pathway along North 30 North, where these waters can be brought back towards the western boundary. Now, this particular circulation feature has been known since the late 90s, but until now, its structure has been poorly explored, and its dynamics is still an open question. Now, once you get to 30 North, the interior pathways looks like quite different, and what we have mostly, and this is mostly known by numerical simulations, in particular by this shown by this particular simulation from Jabal Zhu and colleagues in 2012, is that south of 30 North, we have the deep western boundary current flowing southward, as we know, and in interior we have not only a basin-wide northward recirculation, but a very complex set of localized recirculation cells. And this is shown very clearly in all sorts of eddy resolving simulations. And what we know from the observational perspective is actually constrained to the observations at 26.5 North, where we have an extensive deep western boundary current monitoring moorings since the late 80s. And I want to explore the structure of these recirculation cells as well. So based on that, we built a couple of scientific questions that help us guide some of the results and the research that I'm going to show you in a little bit. And the first one is, what is the absolute velocity structure of the mean North Atlantic deepwater interior pathways in a broader sense and a basin-wide sense, and how this can be best determined from available observations. The second one is more specific, but if the coherent large-scale anticyclonic gyre suggested by Susan Lozier in 1997 exists, what is the role of the deep western boundary current versus the interior pathways in the lower limb of the AMOC in the subtropics? The third one, does the mean deep western boundary current recirculation south of 30 actually consist of multiple localized cyclonic cells as suggested by the numerical simulations? And are these circulation cells eddy driven? And I'm mentioning that because there's some indication that the eddy activity of the deep western boundary current might be related to this process. So we wanted to investigate that as well. So my presentation is divided in two parts. The first part, we are going to try to address in some degree those three first questions, while in the second one, we are going to focus in the recirculation and interior pathways south of 30 north. And the first part has been published in a GRL paper in 2019, where we focused our attention to the upper North Atlantic deepwater part of the lower limb of the AMOC, more specifically to the Labrador seawater domain. Okay, and we have done that with using Argo data. And the idea is to try to, again, better understand the interior pathways of the waters that came out of the western boundary near the Flemish Cap at 50 North, and how it's recirculate around and connects with the quasi-zonal pathway along 30 North. So just to have give you an idea what I have done, and the entire paper is basically describing mean absolute geostrophic velocities at the upper 2,000 meters between 2004 and 2016 using Argo data. And how I built these absolute geostrophic velocities profiles, it was basically, I took the Romanek and Gilson Argo TS climatology to build our geostrophic profiles, and reference that using the Argo drift data from the Omaha 007 at 1,000 decibels. Now, for those who doesn't know exactly what the Omaha data set looks like, is just an estimate of the Argo drift at 1,000 decibels. So we have, every time the Argo profiler goes down, it stays for a while at 1,000 decibels or so, depending on the model of the Argo. And we have an estimate when it comes back. We have the sinking position, the lift position, and then we can estimate the velocity, the deep velocity from those. And we use those. We build we just use a very simple box averaging over the entire North Atlantic to build a mean absolute geostrophic velocity profile like the ones we see here, and where we have the U and V, and the shaded areas are the standard errors of our estimates. 700 decibels, and this is just an example, but approximately for the entire our entire domain, the errors or the standard errors that dominate the uncertainty of this calculation, it comes from this reference level, reference velocity from the Omaha 07. Now, to make our life easy, another thing that I forgot is that the Labrador seawater is not entirely above 2,000 meters everywhere, right? So we had to use another data set to extrapolate our geostrophic shear profiles, and we used the World Ocean Atlas for that. Now, the World Ocean Atlas has way less data than, because just used hydrographic data than the Argo array, but it can give us an idea of the deep circulation. And to make our lives a little bit easier, I'm not gonna look at different depths, but mostly we are going to look at the core, more or less at approximately the core of the classical Labrador seawater at this particular isopycnal surface depth, isopycnal surface of sigma 2 of 36.88 kilograms per meters cube. And we map the stream function from those mean absolute geostrophic velocities along this isopycnal depth. Now, the strength of the circulation, we estimated using transports in the upper Labrador seawater domain and in the classical Labrador seawater domain, following Eric Van Sebille's 2011 methodology, which these particular authors verified that this definition of Labrador seawater encompasses most of the Labrador seawater in a wide range of latitudes, all the way from the subpolar gyre near the equator. Now, this has some limitations, of course. Near the subpolar gyre, we are gonna ended up missing part of the Labrador seawater because it's not completely constrained to these layers. And near the equator, we are going to end up including more water masses than the Labrador seawater. This could be bypassed by using other types of definitions like neutral density, but it would be hard to compare those transports with older estimates that we use to validate our method. So we decided for this, and we can discuss that if you have any questions. So that's basically what I get from that calculation. This is a stream function that we define like this, and where we have local maximum defining anticyclonic circulation, and local minima of the stream function, we have cyclonic circulation. So we can have we can see clearly three areas of circulation, dominated circulation here. One is the subpolar gyre, cyclonic circulation. Then we have in the subtropical area between 50 and 30, we have this anticyclonic dominated area. And south of 30, now we have other cyclonic circulation dominated. So we have those three areas. We have lots of circulation features happening here and being resolved, and I'm gonna go through that a little bit. But one thing that we can quickly see is that since the transect 1 here in yellow is the approximately position of the mid-Atlantic ridge crest, you can see that this anticyclonic circulation is not constrained to the western side of the mid-Atlantic ridge, as we see from some numerical simulations and other older data. So the structure is a little bit different than we knew about it, and you can see clearly a kind of a connection between those waters recirculated here, going to the eastern side of the North Atlantic Basin, flowing southward, and this little point over Transect 2 is the Azores archipelagos, is slowly coming back and connecting with this what seems to be the quasi-zonal pathway. So just to give us a better idea of what I'm talking about in terms of circulation features, this is the same map of the stream function, but now instead of the lines being the stream function lines, the arrows are some of the circulation, the main currents that we found, that we know about in the deep ocean, and how we interpret these circulation patterns. And this white lines are the stretching term of earthel potential vorticity from Argo as well. So we calculated this, and we can see all sorts of things. We can see the deep western boundary current being partially resolved by Argo. We know that Argo has some problems near 2000 meters decibars because how the array was designed, and they don't go to regions shallower than that. We have the deeper part expression, the deeper part of the Gulf Stream, its northern and southern recirculation gyres. We have upper north, the North Atlantic Current. So you can see that there's some kind of a connection between the deep western boundary current streamlines and the North Atlantic Current, and part of this flow is being entrained in the North Atlantic Current and being recirculated around inside the Newfoundland Basin. And you can see that part of this flow is being transported eastwards in the North Atlantic, and this flow seems to be acquiring some potential vorticity. So there's some water transformation going on in this pathway, and at some point, these waters veered southwards, and part of the flow slowly come back to the north of the Azores, but part of the flow is flowing southward east of the Azore archipelagos and returning westwards and connecting with the quasi-zonal pathway. Now, another interesting thing is that in the going back, this journey back to the western boundary, the mean flow is losing potential vorticity again. Now, there are a couple of theories why this is going on, and one of the most interesting things is the possibility. One of the most interesting theories is the put out there by Mike Spall at WHOI, is that how the the Mediterranean overflow waters just above the Labrador seawater layer could be forcing these waters to enter the western part of the North Atlantic, the eastern part of the North Atlantic basin, and going back. So it can generate, and he explains by double diffusion process, like salt fingering process over the eastern side of the basin, and how this can generate input of waters north of the Azores and an output of waters off the eastern part of the basin south of the Azores, which is kind of an interesting take on that. But once we have these waters coming back to the western boundary, what we see south of 30 is this kind of localized recirculation gyres as well, not as well defined as in numerical simulation. This is kind of a noisy field, but you can still see something there. And one of them is called the Abaco gyre, and I'm going to talk about it. And it's characterized by waters being also changing potential vorticity within those areas, which is kind of interesting as well. So just to put some numbers in terms of transport for the Labrador seawater, we saw that most of the Labrador seawater is constrained and recirculating within the Newfoundland Basin, around 9 Sverdrups, and now negative values means southward or westward flows, and positive transports means northward or eastward flows. So you can see southward transport of approximately 9 Sverdrups. However, approximately 3 Sverdrups is flowing east of the Azores over this red part of the domain of the stream function area. Now, if you look at the transport that goes back westward, we estimated the same 3 Sverdrups going westward east of the Azores. So the transport estimates are kind of, they're consistent, and it seems that most of it's flowing right south of the Bermuda Island, around 65 west, around 30 north. So we found that as well. So approximately 3 Sverdrups, it's compared to the transport of the AMOC of 18 Sverdrups or so. It's a small portion, but it's not neglected. It's still a significant amount of water that is not following the deep western boundary current. So just some take-home messages from this. I didn't show the transport validations, but we got good comparisons with regional transport estimates at different areas. And this data set is available if you want to take a look at it or improve. This is a very simple method that gave us a compelling description of the Labrador seawater spreading patterns in the North Atlantic, especially the connection between the anticyclonic circulation suggested by Susan in 1997 and the quasi-zonal pathway around 30 North. And although most of the Labrador seawaters recirculates in the Newfoundland Basin, the trees viaducts that crosses the mid-Atlantic ridge feeds the quasi-zonal pathway along 30 North, as I said. And from the PV distribution, we could verify that a significant water transformation processes are occurring, especially over the mid-Atlantic ridge, which are likely to include elevated diaptichinal mixing processes. Now, focusing on the southern part of the North Atlantic, south of 30 North, most specifically, we're going to talk about the Abaco gyre that I showed before. This also has been published in a JPO paper in 2020, and where our main goal was to describe the mean Abaco gyre structure, which was one of the main structures that we found. And we also chose this one to be described because we have all the observations along 26.5 North and that could help us to understand better the structure of this particular circulation gyre. And I'm gonna get why this particular gyre is so important to be understood in terms of velocity structure. So this is a schematic based on our Argo data, and we're gonna mainly use the Argo data, numerical simulations, and some observations along 26.5 North to understand better what's going on. So what do you use as data? So besides our Argo climatology, we also use CTD, LADCP, and shipboard ADCP profiles obtained during 23 oceanographic cruises between 2001 and 2018 along 26.5 North, plus the moored current meter records between 2004 and 2018 from the regional returning circulation and heat flux array and the rapid programs. Now, the modern layout, which can be seen here in the lower panel of this figure, has been in the water since 2008. So some of the moorings have records going back to 2004, but most of the variability and averages that we're going to talk about, it's between 2008 and 2018. So approximately one decade of data. And to help us understand in terms of variability, what's going on, we're going to use the OFES model from James Tech in Japan, which is a eddy resolving model with a 10th of degree resolution in horizontal and 54 vertical Z levels with snapshots every 3 days between 1980 and 2013. And the approach that we use to study that is basically calculating the meridional velocity, meridional transports along 26.5 North. And in terms of deep western boundary current, we define the total North Atlantic deep water. And now we are talking about the total North Atlantic deep water, not only the upper North Atlantic deep water layer. It's defined, the deep western boundary current is defined as shown here in this green box. Now, these are meridional velocities from the moorings, mean meridional velocity between 2008 and 2018, where you have the Antilles current flowing northward in the upper 1,000 meters and the deep western boundary current next to the continental slope flowing southward. So this is what we define as the deep western boundary current. And every variation is going to be in this fixed box over here. Now, Together with that, from OFIS, we analyze special variations in propagation of the relative vorticity, defined as here, to help us understand the eddies moving around. And when we are talking about eddies, we're talking about perturbations around the mean. So all the time series that we are looking at, we decomposed using a time average plus a perturbation and of the trended series. Although I should say no significant, statistically significant trends were removed, and most of the signal can be reconstructed using this. This Reynolds decomposition type of approach. So let's go jump on how the mean abaco gyre looks like. And the 2D structure was described using Argo and OFIS. So this is the same Argo stream function map that we saw before, but zoom in to our abaco gyre region, and the same region from OFIS. So in the upper row here we have Argo, and the lower row here we have OFIS, and each column represents one depth from 1,000 meters, 2,000 meters, and 4,000 meters. And basically what you can see that OFIS has some consistent structure compared to the Argo, and both of those data sets, they show the abaco gyre getting constrained, more and more constrained. Sorry guys, someone just entered my apartment. I'm sorry for that. So what happens that sorry about that. So what happens that we have the structure of the abaco gyre getting more and more constrained westward of the approximately 774 west, which is where we have what's so-called the Bahama Ridge. I'm going to talk a little about this topographic feature, but it's getting more and more constrained as we go down in the water column near the western boundary. And most of the abaco gyre is constrained from 1,000 and to all the way to the deep, constrained westward of 72 west. So most of the flow is constrained in this range between 77 west and 72 west. Now, how it looks like if you draw a section, get a section, a velocity section from 26.5 north, what do we get? What do we see in terms of vertical structure of this gyre? And here we have a couple of maps. One is the meridional velocity transect from LADCP from the cruises, where we have the little crosses. It's where the average or the mean signal is not statistically different from zero. In panel B here, we have the same transect, but instead of LADCP, we have absolute geostrophic velocities calculated from the CTDs stations, which are these little circles here on the top, referenced with shipboard ADCP's profiles. And panel C is the moorings. So you can see the moorings are just constrained to the deep western boundary current area. And the Argo is shown by this, by panel D. Now you can see that it's really hard and really challenging to quantitatively describe and compare all these different data sets. But what they show is that the deep western boundary current constrained westward of 75.5 west, and the recirculation of the abaco gyre defined in basically two velocity cores, one command kind of bottom intensified here, and here we have the Bahama Ridge, and the upper part in the upper North Atlantic deep water domain, we have another velocity core, a little bit offshore and extending a little bit westward, a little bit more westward. Now, all those data have some sort of limitations. One of them is the number of cruises that that covers the entire line. I have to mention that most of the cruises don't go further offshore than 73 west. So only 9 completed the entire transect. So after, west of 73 and 72 west, you have to be careful, and because significantly less data was used to build this average. And of course, the Argo data doesn't really resolve the deep western boundary current structure, and everything below 2,000 meters is part of an geostrophic extrapolation using World Ocean Atlas. So we have to keep in mind when you compare those data. And just as an example, here we have OFIS, which compares well with the other observations. We have kind of the same structure, but OFIS, it has some difficulties in estimating the transport of the lower North Atlantic deep water due to its underrepresentation of the overflow waters transport. And most of the flow, it's constraining the upper North Atlantic deep water domain above 3,000 meters, for example. And when you compute transports accumulated eastward along that line, you can see these differences pretty well. Now we can see that until we get up to 75.5 west, we see the western boundary current, the deep western boundary current with an average transport of around 30 Sverdrups southward, with an exception of the Argo, of course, because it doesn't resolve the western boundary very well. But as we go east of 75.5, we can see the Abaco gyre northward recirculation part of the gyre, returning these waters northward. Now here in black, we have other estimates from other studies, and ours show a significantly more stronger northward recirculation than the previous ones. But one interesting fact is that if you consider now the AMOC transport, lower limb transport of about 18 Sverdrups, it doesn't matter which type of, which data set you're looking at, all of them show that by the time you integrated the average transport along this line, by the time we get to 70 west, all the excess transport of the deep western boundary current was, in terms of AMOC, was recirculated northward. So the entire, it seems when you look at our Argo data plus these transport estimates, we have a strong suggestion that all the entirety of the AMOC, and this was known before, but now we have a real evidence, a very strong evidence that the entirety of the AMOC now it flows at this latitude, at least, flows southward within the western boundary at 26.5 north. So just to throw out some numbers there, we see the deep western boundary current from all data sets yield a 30 Sverdrup southward, with approximately 6% of this transport being in the upper North Atlantic deep water domain. And between 75.5 and 72, and I'm just talking about 72 here because offshore of this longitude, or eastward of this longitude, the data, we have way less data, and we don't have much reliable estimates. We have these transports that have some discrepancies in terms of Labrador, in terms of total North Atlantic deep water. Although when you consider the upper North Atlantic deep water, all those estimates agree within the errors. Now, it also suggests, especially for the LADCP, that we have to be skeptical when you're looking at LADC freeze velocities at such oligotrophic area where we don't have much of acoustic background scattered to estimate reliable LADCP velocities in the deep ocean. So we have to be careful with that as well. Now, in terms of variability, and I'm going to change gears a little bit so we can have an idea about what are the mesoscales and eddies going around this region. And I'm going to talk about mesoscale and eddies because we found that in another paper of ours that they are very important to force these localized recirculation gyres, such as the Abaco gyre. So here in the upper panel, A, we have the mooring-based transport time series from MOCA, where the black curve is the total 12-hour low pass D-tide time series from the current meters. The red and blue time series is the 40-day low pass filter, and the green one is the 300 days low pass filter. The little dots are the transport estimates from the LADCP because we don't have we are not able to complete the time series with of the deep western boundary current transport using just the moorings. But in the panel A, we have the vertically integrated meridional velocity from WB3, one of the moorings that goes back to 2004, which give us a nice proxy to compare to define the transport before 2008. And what we see that is we have those periods in gray where we have transport inversions. Those are all anomalies, by the way. I removed the mean. The 30s are the mean. That can last from 6 up to 9 months for a long time. So basically, the deep western boundary current seems to be offshore of that green box that I showed before earlier today for long periods of time. And between those big events, our spectral analysis showed that most of the variability and the variance, approximately 40%, is within this particular band of variability between 2050 and 2080 days, with no significant, statistically significant seasonal cycle that could be defined. Now, in the model that we can now analyze 30 years of data, we have kind of the same thing, very similar. We have these big events, big transport, up to 80s variops, anomalous transport, but most of the variance it's constrained between 200 and 355 days of the annual cycle, approximately, between those big events. Now, what causes those big events? It's another interesting question that we wanted to address. And this is the relative vorticity from OPHIS, for example. I hope everyone is seeing this movie, but you can see basically 3 things. One, it's little meanders fastly propagating downward, southward in the domain and crossing the MOCA line. Oops. Some big eddies, big anticyclonic eddies propagating northward against the North Atlantic deepwater average direction, and westward propagating features as well. Now, interesting things is that an interesting thing now, if you zoom out a little bit in the domain, you can see those big eddies. And now this is 300-day low pass filter relative vorticity velocity vectors from OPHIS, showing that those big anticyclonic eddies actually seem to be forming around 20 north, and slowly propagating against the deep western boundary current all the way to 28 north, more or less, where they disintegrate. And these particular large eddies are responsible for forcing this meandering for long periods of time of the deep western boundary current at 26.5 north, which is kind of interesting and completely counterintuitive. Now, in terms of velocity evolution of those big eddies, we wanted to know if we can find some common characteristics in the data and in the model that we could say, okay, there's some suggestion that these large eddies actually happen in the real ocean and is not just a numerical artifact of the model of the simulation. And what we saw that is when we have those big eddies passing by, because the moorings, for example, they just they're just observing the coastal lobe of those eddies. When we have an eddy that is propagating northward, for example, we can see this particular signature in a stick plot like this. So we have when we have northward motion of these eddies, we have this crossing of the vectors when you put in this type of rotation of vectors in a stick plot like this. And both OFIS and velocity observations show kind of the same thing. This kind of the same characteristic, which indicates this might be a real feature in the world's ocean. Now, in terms of what it's forcing the other the shorter time scales, which seems to be related to propagating eddies propagating southward along the boundary. And I say that because we also evaluated all other eddies that are coming from the interior, like Rossby wave, like type of features propagating westwards. And we saw that most of the variability in the model seems to be related to this northward and southward propagating eddies along the boundary within the western boundary. Now, we also made some dynamical analysis, and I'm not going to go into it, but to understand a little bit better of the process that might be generating those data, those eddies, and those smaller meanders, southward propagating meanders. When you look at, for example, the significant, the necessary conditions for instability to happen in the deep ocean, they kind of satisfy. And this is an example of one of the necessary conditions of the horizontal gradient of potential vorticity, airtail potential vorticity, for example. And now that's the complete airtail potential vorticity. Whereas we used some simplified models, such as Rossby waves reflection on slanted boundaries, to try to see if we can reproduce the characteristics of reflected boundary Rossby waves around 20 north and generating those northward propagating. I'm not going to into it, but if you are curious, we can discuss it about it, how I did this. But basically, you consider that there's a zonal or a quasi-zonal Rossby wave reaching the boundary, slanted boundary like this. It's like we have south of the San Salvador spur. I'm going to go back a little bit just to show the slanted boundary here between 26 and 20 north. And we made some, use this simplified, very simplified model, and we were able to predict some of the characteristics in terms of group velocity, phase velocity, and wavelength along the boundary of those wave train, let's say. And they're kind of they're similar to what we see within the model, right? It's still like there are a lot of work to be done here to define exactly what's going on. But just to finish my talk here and about the dynamics that I mentioned in the title, but I didn't explore here too much. We use two different numerical simulations. Again, the OFIS and other simulation using HICOM to show that those deep western boundary current eddies, or at least the deep eddy activity within those time scales, they drive, at least in the model framework, deep western boundary current localized recirculation gyres, all the way from 30 north to 15 north. And we have done that by basically evaluating the mean potential vorticity budget and looking at the different terms and how we, if the eddy driven mean circulation looks like, at least it's similar to the circulation, the total circulation, and what the portion of the circulation is eddy driven. We try to quantify that as well, and also to studying the time scales related to this covariance term here that enters in the budget, the total budget. So we were able to do that using different models in this other paper published in JPO as well earlier this year. Earlier this year, yes. So to finish, a couple of take-home messages here. In terms of mean structure of the Abaco gyre, we saw that there are localized cyclonic circulations as suggested by the Murray, and the Abaco gyre is one of them, where approximately 30 Sverdrups is within the first 200 kilometers from the western boundary, while the total recirculation transport estimates have discrepancies, right? The upper North Atlantic deep water estimates agree within the errors are consistent between 5 and 8 Sverdrups northward. And in terms of variability, we have two main modes of variability at 26.5 north. One are periods around between 250 and 280 days that seem to occur regularly throughout the time series and might be related to those southward propagating meanders as shown by OFIS, and energetic oscillations with longer periods of time, over 400 days, that occur sporadically every 5 to 6 years, where the positive phase can last up to 9 months. And the primary variability is due to this eddy propagating along the boundary and not coming from somewhere else. And I also should say that our analysis showed that these eddies seem to be intrinsic to the deep ocean as well. So with that, I thank you all, and yeah, thanks for listening to me.
Thanks very much, Tiago, for that nice talk. Thanks for sharing your work. So we have time for questions and discussion now. If you have a question for Tiago, please type it in the chat, or you can raise your hand, which is at the bottom of the screen under the reactions button in Zoom. Dan, go ahead.
Hey, Tiago. Really
Hey,
cool
Dan.
talk. I guess I had a
Thanks.
question about the second part of your talk. I wonder if you could talk about the importance of the eddies in training deep western boundary current properties into the interior, and how much that might be for setting the hydrography in that region, and how much trouble you might get into if you had a model representation that didn't have eddies like that.
That's a great question. I haven't looked specifically into in terms of properties, but what we see that it's a very significant homogenization of potential vorticity that we show in the third paper. So over those areas, we have this very weak horizontal gradients because of this eddy variability, and this basically allows the waters to being exchanged between the interior and the western boundary, and they are because of that, they are entrained in these northward recirculation areas, and they form those cyclonic gyres. localized cyclonic gyres, right? Now, now in terms of problems, if you don't have that in a numerical simulation, that's a good question. So basically, when you look at non-eddy resolving models, or at least eddy permitting, where we have a little bit coarser resolution, for example, like 0.2 degrees or even a coarser resolution, we start seeing very different characteristics of the mean recirculation. So basically, you're gonna misrepresent the transports, especially when we try to integrate and look at the AMOC, that is the net transport across the basin, right? We saw that most of it, the net transport is within the western boundary, right? And most of it is recirculating within 700 kilometers or so. So what's gonna happen is that this northward recirculation necessary to explain this the excess transport of the deep western boundary current when compared to the AMOC will be in a larger chunk of the ocean. So not just this little part, this little piece next to the western boundary, I guess I would say that. Now, in terms of time scales for the AMOC variability, I don't know what to say. I don't know if maybe that's what you're most interested in, but I don't know exactly what's going to happen. Yeah.
Okay, thanks. Frank, go ahead.
Hi, Tiago. My question is more related to the first part of your talk, but maybe also the second part, and that is how different are the timescales of these different pathways out of the subpolar North Atlantic? So, you have these excursions going east of the Azores, and whether you can see those differences in transient tracer fields. Can you see a difference in, for example, CFC or SF6 ages of the waters going around the Azores versus the more direct paths in the deep western boundary current?
That's a good question. I know it's still an open question in terms of the time scales. I know from the time that I published this paper for today, there are a couple of other papers that came out looking at this from CG Azul at Hui and Amy Bauer. But this interior pathways can be significantly longer. I don't have the numbers right now in my mind, like how long it can take for this complete cycle of this anticyclonic recirculation of tracers going around. But since we have a lot of recirculation in the area, there were a couple of papers, older papers, showing that the ages of tracers, for example, they are significantly higher, especially over the Newfoundland Basin here. Although most of them, some of those estimates were done in a numerical simulation context, and they seem to be not quite catch this incursions of waters within the eastern part of the basin. So I don't know exactly how this would change, but yeah, it significantly changes the ages of tracers in general. Like they are way older than the ones that goes around, like years of difference.
Okay.
It can take years for this. Now the precise numbers, I'm sorry, but I don't have it here.
That's fine. Okay, thanks.
No problem.
Other questions? We still have time.
If I can ask another question unrelated.
Oh yeah, please.
I was wondering, is there any correlation between what's happening in the Abaco Gyre and what's happening in the Florida Straits? Is there any relationship between the variability of the northward flow in the Straits with what's going on offshore of Abaco?
No, there's not. There's at least not significantly correlation. Well, the Florida Strait is just 800 meters deep, while I'm looking at everything that below 1,000 meters deep in the Abancay Gyre, right? But when you look at the model for and the observations from the MOCA, we see very poor correlation between the deep western boundary current variability and the upper ocean. That's one of the things when I mentioned that those eddies are kind of intrinsic to the deep ocean, is basically we don't have this clear correlation between the upper ocean and what's going on in the deep ocean at 26.5 north.
Okay, thanks.
Some of the big eddies can have a shallower signature, especially south of the San Salvador spur. So I'm gonna go back here. So this little dot is the San Salvador spur here. So those big eddies, they have some signature in the upper ocean, but as it passed the San Salvador spur northward, it loses its correlation. I don't know exactly why. And also the Antilles current, the upper ocean currents becomes stronger here in this area, but there's no real connection between no significant connection between what is going on in the deep ocean and the upper ocean.
Great. Any last questions? Wait a moment here. All right, I think we'll wrap up. Thanks very much, Tiago, for sharing your work for the talk. Next
Thank
week.
you.
Oh yeah, thank you. Next
No,
week.
thank you for inviting me.
Next week for everyone, we'll have CGD